The purpose of this video is twofold. First of all, I want to demonstrate how to solve problems asking you to draw a Lewis structure for a covalent molecule. The methods that I include are how to be sure the structure is correct, B, understanding why certain molecules must have double and/or triple bonds, and lastly, to demonstrate to my students how homework for this type of problem should be formatted. I also want to show my students what was in my lesson today, and the procedures shown here were used for today's Do Now, will be used for today's homework, and will also be used for tomorrow's computer lab. So here we go. You're looking now at what we consider to be the whiteboard in our school, which is Glendale High in Glendale, California. And in that we always include the objectives and the standards. And the standards for state of California is standard 2, and that has to do with chemical bonding. So first of all, I wish to prep for tomorrow's lab. We're doing a molecular geometry lab where Lewis structures and VSEPR are used, valence shell electron pair repulsion, VSEPR. And then I want my students to be able to identify all 5 shapes from the VSEPR theory. Now these aren't all the shapes, but these are the 5 that we require: linear, bent, trigonal planar, trigonal pyramid, and tetrahedral. Now today I wanted my students to draw molecules for beryllium bromide, sulfur dioxide, and carbon trioxide, also known as the carbonate ion. And I threw the carbonate ion in there because the ions are done a little bit differently than normal covalent molecules. So we'll be looking at that. And I want to see columns 1 through 5 of the form that I have used to help my students to be able to do these problems correctly. And let's take a look at one of those forms. Okay, here's a blank form, and in this I have them first draw the molecular formula, and secondly start a Lewis structure where we lay out the atoms without any bonding electrons at all. Then we put in bonding pairs to connect all the atoms, and that's a redraw of what we had in column 2 here in column 3. And the only difference between these 2 boxes would be then that we have lines drawn, which are the bonding electrons, and each line represents 2 electrons. And then we're going to calculate the valence electrons and subbonding electrons, and then we can all put those back into the drawing that's here. And finally, the check step where we need to look and see, do we have all do all of the atoms in the molecule have 8 electrons except hydrogen, beryllium, and boron? And their numbers are here, the 2, 4, and 6. And then we also need to check at the end to see that the total electrons are correct. That's what this form is all about, and you may want to do a rough of this form and use it as part of what we do during the discussion of how these molecules are done. First is kind of an overview, and also to show my students what good homework looks like. I thought that this was the best paper that I got all day out of all 5 classes, 160 students. So this was a really good effort. And the reason I like it is because I saw the molecule, the molecular formula, 1 nitrogen and 3 fluorines. Then I saw the correct Lewis structure with, this is what I was referring to as bonding electrons. And so we have in this molecule, for instance, 3 pairs of bonding electrons, and then we have several unshared pairs, both on the central atom and on the other atoms. And the unshared pairs, this is a little short on the numbers that I wanted, but they at least were working their numbers, and these numbers we'll talk about in greater detail. But the next thing that they were supposed to do with this homework was to show me what is the shape, and it had to be one of the 5 that I showed you before. And here, this is the reason why the molecule has this shape. So that's what I liked about this particular homework page. So, the octet rule again, all atoms have 8 electrons touching them, either shared or unshared. And then we went through electronegativity. Electronegativity is important in drawing Lewis structures because that determines which atom will wind up in the middle if you have 3 or more atoms. And electronegativity applies, what I do is I draw these arrows for trends in such a way that this whole thing here represents the periodic chart. And as that represents the periodic chart, let's see if I can get another arrow in here for us. So as I look at this part here, what we're doing is we're trying to make everybody aware that this blue dot is where you draw all the arrows from, and kind of picture that I'm outlining right now a periodic chart. And so we want to look at the trend for electronegativity. Now it applies to all columns of the periodic chart, not just to the far left column. So as we go up a family, a group, or a column, however you want to refer to them, as we go up, we are going to have an increase in electronegativity. My arrows always point to direction of increase. As we go across into the right, we have an increase that direction, and as we go here and have the trend for a period or row on the periodic chart, it applies to period 7 as well as period 6, 5, 4, 3, 2, and 1. So some students are not seeing that that is important to get that distinction or that understanding, that when you look at an arrow chart like this for trends, it applies to all columns and or all rows, as I was just demonstrating. So let's go down, and the next thing I did was to show how to do the Lewis structure using my method for the cyanide ion. And this is 1 carbon and 1 nitrogen, and it has a charge, which puts it into a little bit of a different category. So what we're going to do is we're going to go ahead and start the Lewis structure the way I always do. So the first thing we do is we draw our carbon and nitrogen in their relative positions, and then we're going to put them in a second time, only this time when we put them in, we are going to put them together. The carbon and the nitrogen are going to be bonded with only 1 shared pair of electrons, like this. And now we're going to go do the numbers. Okay, I took a little pause to build this up a little bit, and what I've just added is these brackets, which is what's typical of all ions. When we do ions, we always put them in brackets when we're doing the Lewis structure. And now the charge here indicates that we have 1 more electron than would be given by carbon, who's in column 4, giving you 4 valence electrons, and nitrogen, who's in column 5, giving you 5 valence electrons. So this little guy says, hey, we got to put another electron in there to show that these guys didn't bring enough to represent what you're seeing inside the brackets. So let's go ahead and add that in. Now what this means is that I've got 4 electrons that came in because of carbon, 5 from nitrogen, and this 1 extra electron up here, because we have a 1 minus charge, would add 1 more electron. Now if this molecule were going to be a positively charged molecule, like the ammonium molecule, which is NH41+, instead of adding an electron, we'd have to take 1 away. So at any rate, this is our total number of electrons, and now we need to put those into the structure, except we already drew one pair of electrons there, so we have to subtract those guys out. Now what I've done is I've shown you when we subtract from the total electrons the original bonding pair, which is here, we wind up with a total of 8 electrons that still need to go in here. And so what I do, and I've given you that same number right here of electrons that we're going to be putting in as unbonded pairs. So let's start putting those guys in. So what I've done is I've put in 2, 4, 6, 8 non-bonding electrons. Okay? And so these guys are what I have put in to make this now all the electrons are in there that should be there. So we've got carbon with 2, 4, 6, and this guy makes 8. Now nitrogen is crying the blues because he's got this pair here and this pair here that are touching him, and that makes him a little shy of 8. In fact, he's 4 shy of 8. So what we're going to do is we're going to have to do some sharing, and this is where double and triple bonds come from, this kind of situation. So we're going to go ahead and take this pair and we're going to get rid of them, and then what we'll do is we will draw in a bonded pair. Okay, as I did that operation, I kept the bonded pair that was originally unbonded in green so that you could see where this pair that's now missing went into the bond. So next I'm going to take this pair right here. I think I'm going to. Let's see if I can get just this pair. Looks like we've got, oh, I see what I've got. Just a second. We're going to get rid of one more of these pairs. Now that that pair's gone, I've got to replace them, so they're going to have to go in the bond as well. Why did I do this? Because let's just put that guy back. Okay? The reason I took this guy out is because I have 2, 4, 6, 8 still for carbon, but nitrogen only has 2, 4, 6. So I've got to get rid of that pair up there on top of the carbon and put them in with the bonding electrons between the carbon and nitrogen. And now you can see I've got a triple bond here. So this carbon now is still looking at 2, 4, 6, 8. You can see the green pairs that those green lines represent a pair of electrons each, and they came from our 8 not bonded electrons, and they became bonding electrons. And then these guys stayed as unbonded. Now let's check the whole thing out. Nitrogen should have 8. 2, 4, 6, 8. Good there. Carbon should have 2, 4, 6, 8. So that part is good, and our total should come out to 10. So we count the total now. 2, 4, 6, 8, and 2 more is 10. So we have just made ourselves a very nice Lewis structure. And in my form of checking things out, the way I have my students do that is what you're going to see right now. So I just added these two numbers here. They refer back to that chart, which we're going to look at in more detail in just a second. So these guys are going to be checked off. Number 1 represents the rule that everybody has to have 8. And we just demonstrated that both carbon and nitrogen have 8. So what I can now do is check this guy off. Done deal. He met that criterion. This second guy here that you're looking at, the number 2, represents the total number of electrons right here, 10. We should have total electrons in here of 10, which I just counted out for you. And so you know that that's good. And now we check this off. By doing these two checks, we assure ourselves that the Lewis structure is correct. Now here's the rules that are printed in my lab And they're also here to introduce my students to the rules that we're going to be used. No unshared pairs on the central atom. No unshared pairs on the central atom means exactly what it says, and we'll look at that right now. No unshared pairs on the central atom applies to linear and to trigonal planar. Now, as we look at this molecule right here, this is a linear molecule. Why? Because there's no unshared pairs. That's guys like these, unshared pairs on the central atom, which in this case is beryllium. So, because there's no unshared pairs, this guy can stay straight, and no unshared pairs are going to bend the molecule. And we'll talk, we don't have time in the video here to talk about that whole concept. But suffice it to say that this rule does work. And this is also a linear, and the reason that this guy is linear is because it only has two atoms. It has unshared pairs, and there is no central atom. So linear can be either 2 or 3 atoms. And this guy is a linear, and it's because there are no unshared pairs on the central. And this guy is linear because he's only 2 atoms. And you could even make a little note in here to add that to that rule if you wanted to so you don't forget. Now, the next thing is 4 atoms around the central atom make a tetrahedral, and then the third one is unshared pairs on the central atom apply to both bent and trigonal pyramid. And so we're going to go through how we did the shapes and the molecules for our do now, and here we have it. We did beryllium chloride, and these are actually student scratches that were done during my 6th period today. So in this case we drew beryllium in the middle, so he's right there, and we had bromide on either side. Now when we first drew this, we only put in these guys right here. So we had beryllium with 2 atoms, or 2 electrons, 2 valence electrons, because he's in column 2. And bromine had 14 because each bromine carries 7, and there's 2 of them. So our total number of electrons to deal with in this molecule was 16. And when we take out the 4 here, this is a 4, you can't tell for sure, but the 4 comes because there are 2 here and 2 here. So we look over here now, and when we subtract them, we get a total of 12. So we had to put 2, 4, 6, 8, 10, 12 on the bromines, and beryllium didn't need any more because in a Lewis structure he only needs 4. So that's what that rule stuff was all about. Now as we go back and check this out at the end, we check rule number 1. Rule number 1 was all have 8 except hydrogen. Well, this bromine has 2, 4, 6, 8. This bromine also has 2, 4, 6, 8. But beryllium doesn't, but he's our exception. He only has 4. So we can check off rule number 1. Rule number 2 got checked off because the total electrons counted up to be what the 16 number was. So we had 8 around this bromine and 8 around this bromine. The 2 together total up 16. And that gives us a total of 16, so we are sure that that one matches. So this is a good Lewis structure. So we carry on and do the second. So to continue to the next molecule, the SO2, we laid it out, just the atoms, in roughly the shape that we think it's going to be, and then we put the bonding electrons in. So before we can go any further, we do the totals. Sulfur, column 6, brings 6 valence electrons. Oxygen, there's two of them in this molecule. Normally we put a little subscript in there, and I'm going to go ahead and add that right now. So this should be a 2 in here. That reminds us that we had 2 of the oxygens, and 6 each gives us 12. So that's why the 12 is over here. This student did it a little different. And when we add those up, we get 18. Now we have to subtract the original bonding electrons, which are only one line between this sulfur and the oxygen, and one line between this sulfur and this oxygen. So that's why we only subtracted 4. You're seeing 6. But that got added later, because when we realized we had 14 electrons left, and we gave out 2, 4, 6, 8, 10, and 12. There's the 12 up there. You can see those little guys. And now the reason that this got, the extra bond got in here, is because sulfur was short. Sulfur did not have only, but let's see, he had this guy, 2, 4, and 6, and when we add this guy in by taking 2 away from oxygen, which we did earlier, we wound up with a double bond over here, a single bond here, and we now have 2, 4, 6, 8 electrons on this oxygen, 2, 4, 6, 8 electrons on the sulfur, and 2, 4, 6, 8 electrons on this oxygen. So everybody has 8, and that allows us to check off rule number 1. Now we have to check the total out, 18 total. There's 8 around this oxygen and 8 around this oxygen. 8 and 8 are 16, plus the 2 on the sulfur makes a total of 18, and now we can check off number 2. The total electrons come out right. Now, here's another Lewis structure for a molecule that has a charge, and that becomes an ion. So first of all, we laid him out like this, and with this layout, we have the general form of the molecule. We add 1, 2, 3 single bonds. This guy came later, and we have to draw a bracket, and we also have to show the charge for the ion. And so this guy turns out to be carbon with 4. Carbon brings in 4, that is, and oxygen, 3 of them, bring in 6 times 3. 6 is the column that oxygen is in, for a total of 18. And so when we add those guys up, we get 22. Now, like we did with the cyanide molecule, we added 2 electrons because there was a charge up here of 2. So the 2 extra electrons give us a total number of electrons that we have to draw, that we have to put into the Lewis structure of 24. Now originally we just had 2, 4, 6 bonding electrons, so we took those out, and that left us with a total of 18. And let's make this a little bit easier to work with. Alright, so we got 18, and so those 18 are the guys that you're going to see here. The one extra that we got here, 2, 4, 6, 8, 10, 12, 14, 16, 18. That accounts for all of these guys. Now, one of those unbonded pairs became a bonding pair because carbon didn't have enough electrons. But now carbon does. So let's see if everybody has 8. Oxygen here, 2, 4, 6, 8. Oxygen over here, 2, 4, 6, 8. Oxygen down here, 2, 4, 6, and 8. And carbon has 2, 4, 6, 8. So we can check off rule number 1. Everybody has 8. Now here's the total. 24 is what we should have. And we have 8 around this oxygen, 8 around this oxygen, and 8 around this oxygen. So 3 times 8 gives us a total of 24. And that works to give us our total here to be able to check off this rule. Now, the next things that I did was I wanted to show a comparison between molecule models and how we write them. And first of all was the linear. The linear is chlorine and a hydrogen, for instance, Now you don't see the unshared pairs for the chlorine here. But if you look on the actual model, you'll see 1, 2, 3 unshared pairs. So here we see our linear molecule with only 2 atoms. Here we see a linear molecule with 3 atoms. Now this is how it looks on paper. The actual models are quite different, or a little bit different anyway. And so we see the unshared pairs 1, 2, 3. We see shared pairs here, and here is an oxygen, this would be a hydrogen atom, and the guy in the middle here is a chlorine atom, which is going to be represented in green. Now here we have something like carbon dioxide, or carbon monoxide, either one. Not carbon monoxide, just carbon dioxide. Carbon dioxide would look like this, only there would be 2 unshared pairs here and 2 unshared pairs here. Or this could be carbon with 2 hydrogens. That would be even better to visualize this with. So carbon and 2 hydrogens, and that represents, or beryllium, as I've shown here, beryllium with 2 hydrogens. And so if we take this guy right here for a beryllium atom with 2 hydrogens on either end, we can see the comparison between an actual model and the way we draw them. Now here's a Vesper trigonal planar over here. Okay, Vesper is valence shell electron pair repulsion. And so trigonal planar is like boron in the middle, who's an exception, and hydrogens around him. He only needs 6 valence electrons in a Lewis structure. And that's why we see him in this picture over here with a carbon in the middle and hydrogens around it. Not carbon, but this would be like chlorine. No. This would have to be beryllium. Boron. Boron is the guy. Yes, that's what we showed you in the last model. So I finally got it right, and that represents our trigonal planar. And here's the comparison now for the last 2 that I hold my students responsible for. And you see carbon with 4 hydrogens, also known as methane. So methane would have your 4 hydrogens here, 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 and here. This guy represents the hydrogen going back behind. This guy represents the hydrogen coming up front, which is hard to show in a 2-dimensional space, where the model shows it much more elegantly. And now you can see this tetrahedral molecule here. And that would be carbon with 4 hydrogens around it. And then back here, we also have a bent molecule. Let's get the bent up in the view here. And with a bent molecule, we have oxygen in the middle and 2 hydrogens, also known as water. But you see these 2 unshared pairs. Well, it's kind of hard to get a visual on that, so when we look back here at this drawing, or at this representation of a picture of a bent molecule with our model set, we'd have an unshared pair here and here, which makes it look a little bit more realistic. Here's our shared pairs, and here's our hydrogen, and the oxygen, the oxygen is here in the middle. Now, as we go up to trigonal pyramid, you can see very nicely here how the trigonal pyramid is laid out, very similar to the tetrahedral. So we've got the unshared pairs, just like we did in the shared pairs. They're the bonding electrons, here, here, and here. Also here, here, and here. And the unshared pair here would be similar to this, except there's no atom like you see here on the tetrahedral. This guy just has an unshared pair. This, of course, is another shared pair. So the trigonal pyramid, as you look back here, would be represented on paper this way, with the oxygen and 3 hydrogens? No, that wouldn't. Well, that could be. That could be. The oxygen would need to have a total of 8, 2, 4, 6, 8, and there would be 3 hydrogens, H3O. Okay, and that would work with this guy. So the trigonal planar would be this guy. So you've seen everything that I showed in class today. I hope this is beneficial to you.